Just a quick look at a thing called expected value. This comes up in both the probability externals, so it's a bit of a crossover. This is used when we're applying a probability to a number of individuals. On a simple level, if we think of a basketballer who shoots an average of 80%, which is pretty good, I understand, and that basketballer in a game takes 15 shots. In terms of estimating how many we would expect them to get, well, we would take the probability, we would times it by the number of shots, and so 0.8 times, or 0.8 of 15 is 12. So we would expect them to get 12 shots in out of 15. That sort of thing is applied in more complicated ways around. Sometimes you're going to have to deal with a table. And so you might get something. Now, the 4-key problem we'll look at another time, but the problem, if it's based on a person having 4 keys that are unmarked, they have to get through a gate and then a door, and how many keys will it take if they are done completely at random. Slightly ridiculous context, but so they have a 4 out of 24 chance of getting through with 2 keys, so both are right. A 4 out of 24 chance of getting through with 3, and the remaining, far more likely situation is that they actually need 4 keys and get through the second door on their last key. Now, in this context, the expected number of keys needed, it can also be considered the average. So the average number of keys needed over a lot of times through this trial, because sometimes you get it in 2, sometimes you get it in 3, sometimes you get it in 4. But if we average them, and we've done it a heap of times, we would get an expected value. Now, the expected value comes with a beautiful formula down here in red. It's a bit of a highlight, perhaps the highlight of the clip. And E of X stands for expected value. This little doofer here stands for the sum of, so add them all up, and each X value times its probability. So in this case, if the working is more simple than it appears actually, so if I do a bit of highlight in there and bring that back, this is what it would look like to find the expected number of keys, or the average over a lot of different times through. You take each value, each X, and times it by its probability. So that's the first one. 2 times 4 over 24 plus another possibility. 3 keys times 4 over 24 plus the final and most likely probability, 4 times its probability. If I add them all up, and I can do this on a calculator one way or another, the answer comes to 3.5 or 3.5 keys. So I would expect on average, if it was simply done randomly, to use 3.5 keys or 3.5 keys to get in through both the gate and the door. Okay, and